Hey guys, back with another video, and today we're talking about speakers. So speakers are the primary way we listen to music today. Even in live performances, most of the sound we hear is coming from speakers. And of course they go beyond music. Speakers are used when you take a phone call, when the bell rings at your school. They're used for all long-distance verbal communication. Think about that. Every single instance of long-distance verbal communication, there's at least one speaker involved. Probably multiple. I mean, just look around you. How many speakers are there right around you? If you can see other people, they probably have phones, and their phones probably have one or two speakers. If you're in a room, maybe you have a laptop, or maybe you have a tablet, and you probably have your phone. Maybe you have earbuds, maybe headphones. All those things have or are speakers. Speakers are everywhere. But not many people actually understand how they work, how a circular disc vibrating back and forth can very accurately recreate a sound. Well, first a little review from my video about dissonance, about what sound is. Sound itself doesn't look like what you see on a waveform. This is not sound. This is actually a much better representation of what sound is. Sound is the oscillation between high and low pressure in the air. It has to be at least 20 hertz, meaning that oscillation has to happen 20 times a second before you can hear it as sound. But when it goes that fast, you hear it as sound. So in this picture, you can think of the black bars as high pressure and the white between them as low pressure. And that's actually a pretty good representation of what sound is. Of course, in real life, it's not distinct regions of high and low pressure. It's a gradual change. That gradual change that's modeled by this lovely sine curve here. But it's a pretty good representation. As for a waveform, when the waveform is in the middle, that's the speaker at rest. That is zero pressure, essentially. That is the speaker providing zero pressure. When it's at the bottom, that's low pressure. That's making the air pressure lower, and at the top, the air pressure is higher. And that's how that works. Now, what that means in terms of a speaker, what it's doing, it's pulling back to expand the air and create low pressure here, and it's pushing forward here to compress the air, making it higher pressure. Now, low and high pressure in sound that we hear is actually very tiny compared to the atmospheric pressure on the surface of the Earth. Our ears are just really sensitive, mind-bogglingly sensitive. Some animals are even more mind-bogglingly sensitive to pressure changes. But this sensitivity is also the reason why even fairly small changes in pressure, such as those in airplanes, can cause considerable discomfort. But let's get to speakers. So here's the innards of a speaker. You have a coil of wire, which is above a ring-shaped magnet. In this design, some designs have a bar magnet that the ring is coiled over, but the coil is attached to the diaphragm, and it also has a suspension, which we'll get to in a bit. You have the dust cap, which is that little dome in the middle, which literally just is to stop dust from getting inside of it. So a current goes through the wire. This is how you actually get the diaphragm to move and make sound. A current goes through the wire, and since it's in a coil shape, for fancy physics reasons, when wires are in a coil shape and a current is run through them, they create a magnetic field. And so you can manipulate that by flipping around the current, which is changing which end of the wire is positive and which is negative, and then also slightly varying the voltage, doing these things thousands of times per second, to attract and repel from the magnet to make the diaphragm move in such a way to produce sound. So yeah, that's how you do it. Now, a little problem arises in balancing that sound out, because magnetic force, it gets stronger as the two things get together, and actually by a lot, because it's an inverse square law, meaning that twice as close is 4 times the strength, 3 times as close is 9 times the strength, 4 times as close is 16 times the strength, etc. And so as the coil gets closer, it would actually also increase its force by a lot, and thus its speed, and therefore give you an incorrect sound. The suspension, also known as the spider, is there to balance that out, so the amount of force between the coil and magnet stays constant. Springs, which is what the suspension is, happen to also follow, and it's not an inverse square law exactly, but it is based on the square of the distance that you move it, which basically means that it's a perfect fit to counteract that magnetic force. And if it's calibrated properly, which it has to be, then it can perfectly counteract that, and you get a really good sound. And that's actually one of the things that determines the quality of a speaker, is how well calibrated that suspension is for the magnet. And of course, there's lots of other things that determine quality, but that's just one of them. Now, on to volume. Bass versus treble specifically, and big speakers. Why do we need big speakers? Well, short and simple, the reason is amplitude is not equal to volume. It's not. Amplitude is not equal to volume. Amplitude is proportional to volume. But you also need to factor in a few other things. The formula for volume is this: 4 times the frequency times the area of the speaker times the amplitude, and then times some constant number to get you to units of volume. But let's go through that a little bit. So volume as we perceive it is according to how much air is being moved in a given amount of time. Amplitude is proportional to how much air gets moved in a second, but think about this. If you have a 400 Hz signal and a 200 Hz signal, both through the same speaker and both with the same amplitude, the 400 Hz signal will move through that amplitude twice in the same time that the 200 Hz signal will move through it once. Therefore, the 400 Hz signal will move twice as much air and give twice as much volume. So the reason you need big speakers to get bass is to have more area to compensate for the lower pitch not moving as much air. Now, this is all about real volume, which is how much air is actually being moved. But, of course, we're humans. We have to be different. So we perceive sound on a logarithmic scale. So a doubling of the real volume will only multiply the perceived volume, what we hear, by 1.3. And you can calculate this with this equation. Log base 10 of the real multiplier plus 1 equals the perceived multiplier. And 10 to the power of the perceived multiplier minus 1 equals the real multiplier. So, a couple examples. If you multiplied the real volume by 10, you're moving 10 times as much air, the perceived increase would only be 2 times. It would only sound twice as loud. And if you wanted to make it sound 4 times as loud, you would need to move 1,000 times as much air. Pretty crazy. Just in case you didn't get it, volume, as in the loudness of a sound, is the volume of air that you move in a given amount of time. So, just in case you didn't get that the first time. I didn't get that the first time when I learned about this stuff, so there you go. Also, I didn't explain the 4 from the volume equation. The 4 is because the amplitude is the distance from the midline to the peak or the minimum. And so you go through that 4 times when you do an entire oscillation. 1, 2, 3, 4. And that's where the 4 came from. If you took it out, it'd still be proportional, but there it is. Yeah, there you go. There's speakers and how they work. So I post videos about music theory and sound theory every Thursday. So yeah, thanks for watching. Bye.